Hi everybody, this is again another example of interfacing a digital sensor to your AVR microcontroller. Today what we are trying to do is learn more about a temperature and humidity sensor, a 3-pin device, which use single wire transmission for communication between the AVR and the sensor. So this is DHT 11 sensor. Um, and it has the capability of measuring the humidity from 20% to 90% relative humidity and temperature in degrees Celsius in the range of 0 to 50 degrees. So if you wish to measure a temperature beyond 50 or lower than 0, this is not an ideal sensor. But if you're thinking about this temperature range and the humidity level, you can still use this one. So it comes with the 4-pin device. So today I'm going to use this web link, and they have an example coding, and so I'm just trying to explain you about how to interface this sensor and how to write a program in Atmel Studio using this web link. So this is how it's going to be interfaced with Atmega 16 or Atmega 32. And we have LCD display to display the temperature and humidity. So as you could see here, the pin port D, pin 6 is connected to the data pin of the sensor, and the VGG is supplied with 5 volt, and ground is connected to the ground, and pin number 3 is not connected to anywhere, so you can left it floating. And make sure you should pull up this data line with at least 4.7K resistor to 5 volt line. So which means like this line is always at logic high level. So LCD, now this is a 4-pin configuration, so you just need to use 4 pins for data and 2 pins for control, and it's a 16:2 LCD. And this is the coding for that for this temperature and humidity sensor, and they have a demonstration of how it works. So if you can see here, so humidity is shown in the 0th row, and the temperature shown in the bottom row. So temperature is in degrees, and since this is trying to get close to like a electric bulb soldering iron, so in that case the temperature increases. So this works fine. So even I have tested this code and it works fine. Before we move into the coding of this project, I would like to explain you in detail about this, how this sensor works. All right, so now I have opened the data sheet of this sensor. So I will make sure that available of all these documents and links via LMS. So this is the so this is a one wire communication, which means you have a single wire for communication between your microcontroller and the sensor. So this is that data line. You can connect it to any digital pin of your microcontroller. And so the data format it has 5 packet of data, which means so this is packet 1, 2, 3, 4, and 5. So first data packet is 8-bit, which is a 1 byte. Second one is again a byte, and all these 5 some data packets are bytes. Now the first byte represents the humidity, high humidity, and the second byte represents the low humidity. Basically, these first 2 bytes are for humidity, and the next 2 bytes are for temperature, and final byte is for parity, or which means the error checking of this received data. If the data is corrupted, you can check from this parity bit, and ignore if any data packet is corrupted. Now when it comes for humidity, so you have two bytes. The first byte is the integer value. For example, now if we say the relative humidity is 50.25, so the integer value represented by this byte and the decimal value is represented by this, right? So they send it separately, so you have to use some kind of calculation or display these numbers separately via LCD, separated by a dot. But basically, this is the integer value and this is the decimal points for the humidity, and same format is followed for the temperature as well. And now we can take a look at this parity bit, which is for error detection. So the parity is calculated by so they send in the parity. So this is the data packet sent by the sensor. So the sensor itself collect at all these four packets, like the data packets, the temperature and humidity, and make a value which is equal to this parity. So you can see here now these four samples here. So the last bit is 1, 0, 0, and 0. So 1 plus 3 zeros is 1. And second one is 0, 0, 0, and 0. All are 0. Third one is 1. And here 0. And here 0. And here 0. And it is 1. Likewise, so it is done by the sensor itself. It is sending, adding all these four bytes together and making a parity bit. And when you receive this data from your microcontroller, so if your program is running well and your hardware is running well, I mean, everything is done with some kind of a precision timing. So your AVR also has a clock generator, the oscillator. So it has a timing, and the sensor itself has some sort of timing. So both timings of these two devices should be matched. For example, if this guy generates like a 20 microsecond delay, and that should be equals to the 20 microsecond delay generated by this guy. Due to any temperature deviations of the ambient or any other changes, due to the inaccuracy of the internal oscillator or some deviation, so these timings might not be accurate. Like sometimes your microcontroller will generate a 80 microsecond delay, even if you write 20 microsecond in the program, right? Due to the hardware inaccuracy. In that case, the data might be corrupted when you're reading it. But the sensor will always send these four packets and the addition of all these four packets. So when you read all these four packets, so from your program, so you can add them in your code, right? So you add in your code, and if that number is not equal to what you read by this one, so definitely there's a problem in your data. So you can ignore that data packet and request it again. So if it happens again and again, so you have to make sure there's something wrong in your, either in your code or in your hardware. So you have to debug it for and clear whatever the bug is in your system, right? Now in this case, so this is a parity bit, which means like when you add all these four, it should be something like that. But when you receive data shows something like this. Okay, so there's a this is the received data. There's some sort of error in your received data. For example, now if you take a look at this one, and now this is what you the sensor is generated. So this one, the second example, this is the sensor generated parity. And when you collect all these received data packets, so you should end up with this value. And this value and this value are not equal. You can see the third 0, 1, 2 second bit here is not same as the parity bit. So definitely there's some problem. Either it is caused due to the sensor or some sort of inaccuracy in your AVR microcontroller or in the data line. So you can ignore that one, and you can request another data packet and ignoring the corrupted data packet. Now this is how the data looks like. So this is a single wire data transmission. So like in the 2-wire transmission, it is easy to use ones and zeros using a clock generator, but in this case we don't have a clock. So everything has to be done within this single wire. So to initiate the data transmission, like handshaking, so your microcontroller, the AVR, has to pull this the data line down at least 20 milliseconds, right? So you pull this line down and you release it. So when you release, it will keep some time on logic high. Then the sensor will pull the line down again, telling, okay, I am ready for data transmission as a response signal, and keeping it low. And again, it will release that line, right? So this is like a handshaking. So your AVR will generate this pulse, and your sensor will generate this pulse. So like a handshaking. So your sensor is ready for transmitting the data. So then it follows this data packet. So this 5 samples or 5 packets of 8 bytes, and then it will the sensor will release the line, which means the line will goes to logic high. So if you need another data packet, so your microcontroller needs to pull the line down and follow this period, and then the sensor will respond and transmit the data. So how to transmit logic 0 and 1, because this is this when the line is down, we know like it is 0, and when the line is high, it is 1. So how to realize logic 0 and logic 1, or bit 0 and bit 1? Before that, I would like to tell you, in the initialization process, you have to pull this line at least 80 milliseconds. So typically we keep it around like 20 milliseconds, considering any deviations in the clocks. And then your sensor will generate this kind of a response signal, and then it will start transmitting the data. So to realize the bit 0 and bit 1, so it is something like this. The bit 0 is represented by a delay of 50 microsecond turn off period, followed by 26 to 28 microsecond on period, right? And if the bit 1, when you want to consider it, so it is 50 microsecond turn off period and 70 microsecond turn on period. So if this turn on period is longer than the turn on period of this one, definitely this is representing bit 1. So the turn off period is same for both bits, right? But the turn on period is greater in the bit 1. So here it is around up to 28 microsecond, but in bit 1 it is 70 microsecond. So in your program, so you can identify data 0 or data 1 by looking at the duration of this high pulse period. Okay, so that is all about the data sheet. So then we can move to the program, which is example program shown in this web link. So in this program, so there are a few functions defined. The request, that is requested by your microcontroller. So this is the request response. So you have to keep the line for 20 microseconds off. And then the response is done by your sensor. and this is a response period. And then you can read the data using this function. So that function, what it do is after the response, so this data packets coming for like 40 bits, which means 8 samples of sorry, 5 samples of 5 samples of bytes, right? Altogether 40 bits, 5 bytes. So that is read by this function. And then we have the main function. So they are using a LCD library. So the library is defined here. So you have to include the external library. I will show you how to use the external library file. And all this data, so they reading the high value, integer value for the humidity and the decimal value for the humidity. So those are copied to unsigned integer 8, which is like same as the unsigned short, right? So 8-bit. And so integer value of humidity is copied by reading using this function. And then the decimal value also read from that function. So you have to follow a sequence like reading the humidity high is decimal and temperature high is decimal and final the parity. So that is done by following this, calling the same reading function 5 times. And if this, when you add these 4 numbers, it should be equals to the parity. So the parity is read as checksum here. So when it is the sum of these are not equal to checksum, you can display an error message on your CD, which means that the data is corrupted. Otherwise, you can starting the displaying the data. In this example, so IRH is an unsigned integer. You can see here it is an unsigned integer of 8-bit. And so the LCD is accepting only strings. So in that case, they are using integer to string converter I to A. And so they have defined this data as like a char array, right? And then use the number format as decimal, number 10 format, and convert. And then you can, like, this value what we read from the sensor IRH is uint A, but you have to convert into a string before you display on the LCD. So in that case, I2OA function is called. So I2OA is something like that. So it is like a converting integer to a string. So for example, now here, so I2OA and integer I, and buffer is some sort of char buffer of length of 33, and the number format is 10. So then it will show this decimal value as 1750, right? So same thing is done here. So this is your variable, and this is the data is this char buffer you define here. So the length of 5 is enough here. You can define up to 33 as this example, but it is too much consuming memory. 5 is enough for our application. So then it will convert this variable to a string with the decimal base and display on the LCD. And after that, it's showing a dot. You can see here, like starting with the displaying humidity from the initial point, humidity, and then temperature equals in the other line. You can see these two are printed at the main function, right? And then displaying the data and the high value, and then dot. You can see this is the high value, and then dot, and then the decimal value, and finally this percentage symbol, since it is related to humidity. So in printing, so the LCD goes to the 11th location of 0th row. So you can see here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 55 is starting from the 11th location. And this one here starting from this 35 start from location 6, right? That's why it is asking to go to print starting from this point, because temperature equals and humidity equals are already printed before you start printing the real data. It is done in the main function. So that is all about displaying the data. So the reference link for this IO2A is here. I will share this link. And now we can take a look at how we going to done this reading the data from this sensor. So if you take a look at this void request function, so that is for this part of your code to request the data. So it has to be some delay of more than 80 milliseconds. So if you move here, so first thing is you have to set your port pin. In this case, you are setting it as output, so you have to pull the line down, right? So you are not reading anything, so you are making it as output in order to pull this line down. So data direction is of DHT 11 pin is defined as pin number 6, right? So pin number 6 of your port D, you can see here PD6. So data direction is set to high, which is the output, and you are clearing port D here. Clear this bit means making that port pin as logic 0, which stand for making this kind of logic low from the line, and keep that logic level low around 20 milliseconds. So the recommended value is higher than 18 milliseconds, so we are keeping 20 milliseconds delay. And after that, we are releasing the line again, which means like we are making this set this pin high, right? So which means this part of the signal. So we initially the line was at logic high, we did nothing, and then we pull the line down for 20 milliseconds, having at least 2 milliseconds more than the recommended 18 milliseconds, so 20 milliseconds off, and then we set the line high. So that part is done. So that is the request from the sensor. So representing this part of the cycle. So this is done as handshaking by the AVR. Then the response by the sensor. So that is this part. So this part of the code is for response. So now we have to read the data. So now this part is done by the sensor, so we can't do anything. So we just can wait, sit down and wait and listen. So in that case, we are going to read the data coming from the sensor, right? That is the response signal. In the response, so data direction is now as the output. So the as the input. So now this pin act as the input. So you are clearing that data direction of pin number 6 of port D, and you are just waiting in a waiting to read the data. So if the data is high, right? So this line, right? So keep waiting here, and so after some time, this you don't know, like so this is the one that we have done up to here, right? So we set the line high, right? We set the line high, but we don't know when this sensor will react. So the sensor can take longer time, or we don't know this time, right? So the sensor might take longer time. So we have to just wait, reading this logic high state until the sensor pull the line down. So in that case, so we set it as an input and keep looking at this logic high state and just waiting here. And then again, when the sensor pull the line down, so we are waiting until this during this period in a while loop, right? So we are just reading and waiting until this line is 0. And again, then the sensor will release the line. So again, there's a logic high level. So we have to again wait in this logic high period in a while loop. So until this line is at logic high, it is circulating in this line, right? So that is the response part. So we have the request up to here, and then the response up to here. So then it will start transmitting the data as you request. So the first request is in this while one loop. So we request and the response, and then receive the data from the integer value of the relative humidity, IRH. So that will call this receive data function. So this function returns uint 8, which is like an unsigned integer of 8 bits, same as the unsigned short, right? So it's a returning a value. So return value is C. So C is defined as, again, as unsigned in uint 8t. Initial value is 0. So once the data is read, so it will return that value. So it is copied that value. When you call this function, it will copy that to integer of the IRH directly to here, right? So calling the function means returning that data and copy it to this variable. So returning value is C. So it has a for loop. So in the for loop, so it is done for 8 times. So now we have to distinguish if the data is 1 or 0. Okay, so first is if you take a look at this bit 0. Bit 0 is something like this: 50 microsecond off and around 28 microsecond on. And bit 1 is 50 microsecond off and 70 microsecond on. So in this code, it is just waiting in a while loop, reading this pin number 6, PD6, reading it in the logic 0 state. Okay, and it will wait until this during this period, 50 microseconds. So you don't need to define any delays or anything. So it is just in this while loop until this goes high. When it goes high, so it is exit from this while loop, right? Until this line is logic low, it will remain in this while loop. Once it goes to high state, it will return from this while loop. And then we are now waiting for 30 microseconds doing nothing, which means like, so we are waited here. We have been waiting here, and then we jump here, and then again we waiting for around like 30 microseconds. So if it is logic 1 also, we are here and we are waiting for 30 microseconds. Altogether, we are at a level of here or here, right? Now you can see here, if we take a look at the back here, now we are reading this pin state, pin T, and reading this logic level of this PD6. And at this point, if the data packet was a 0, you should definitely read it as 0, because this point it should be 0. 28 microsecond up to it is high, and 30 microsecond is somewhere here, so it is 0. And if it is a logic 1, you are still there is enough space for 40 microseconds, so you are still at logic high. So which means When you read after 30 microsecond, if it is a logic bit 0, it will be 0. If it is bit 1, you will get high, right? So that's how we're going to read it as a bit 1 or 0 using this function. So if the bit is 1, so what we do is we shift to the left one time and or with 1. Otherwise, which means this kind of condition, if the bit is high, we consider it as a bit 1. So what we do is we take the C variable and shift it one time and or with 1. And otherwise, we just shift it to left, right? And then if that pin is at logic high, so we have to keep waiting until that until it is goes to somewhere here and restart from here up to here, right? So if it is 0, it will just ignore this line. If it is a bit 1, you know, like there is some remaining part of the signal that is logic high, so you have to wait until that signal high line is clear, right? So this thing you have to just keep understand, because that is to do this for 8 times. All right, so now this is my C variable. It is initially at 0. For example, let's say like we just found a logic high state, right? In that case, what is this is left shift this C variable one time. So it should be something, this is the C variable. And when you shift it one time, it should be, looks like again as something like this. So you shift it one time. So, and this one will overflow. This one will go out from the out from this line, and the remaining will be filled with the 0 again, right? And you just make a OR operation with this shifted line. So the OR with 1. 1 means again that data packet should be something like this. 4 zeros and 1. Okay, so now after shifting, so the new so after this operation, so the new value of the C will be same, right? Because after shifting a 0 and copy that 0, filling the remaining with the 0 will be the same. And you take OR operation, so you know, like when you OR this with the 1, so this will be 1, all the others will be zeros. Okay, and if that is a 0, like a detected bit is like if the bit is 1, this will be something like the what after doing this command, so the C variable changes to something like that. If it is a bit more 0, so it will be all zeros. It is just left shifting and copying this one, and it will be all zeros. Okay. So now the for loop is done for one time, and again it has to come in this row when the next bit is received. Right. Now we have just read one bit, and the next bit also you have to do it until you read all eight bits of this data packet. Okay. Now let's say now when it comes again, so now if it is a bit 1, so the first bit was a 1, then it is like that. If it is again the next bit also is a 1, so you just left shift here, and or with 1, and it is updating. I mean with every bit that you're receiving, whether it is a 1, it will update this one and shift this bit to next, and likewise. So after 8, once this for loop completed, so the first bit that you received will move to somewhere here. So it is somewhere here, right? And the next bits are following that. So which means this is a MSB, right? So MSB means like you are just reading this first bit. So the first bit comes here, right? And the following the next bit. So the first operation done and shifted, and likewise. So after 8 operations, so the first bit that you read from the signal will be shifted to somewhere here. And that is how it is done. So after running this for loop, so basically you have just read the data packet related to any data packet, either it is humidity or temperature or the integer value or decimal. Okay, so those values will be copied to these variables and converted to string and copied on your LCD. And so you don't need to read it without any time gap, but it is better because, you know, like the temperatures and the humidity does not update instantaneously. These are slowly varying variables, so you can make a delay before you starting sampling the next data packet. 10 milliseconds will be okay. Even you can make a delay like 1 second will be okay, right? So that is basically how this happens. But interestingly, these guys haven't defined any settings for the LCD. Instead, they have included this LCD library, external library. And so they are calling this header file. And also, if you want to use this I2OA, integer to string conversion, before you printing on LCD, you have to call this, include this stdlib and stdoh2 headers, like in this I2OA reference, right? So otherwise, you will get some compilation errors. So I have just tested this one, and even it works fine in Proteus. So you can try this code and build this one on Proteus. The Proteus has this DHT 11 sensor, and you can use that Mega 16 and 16 by 2 LCD. So you can get this working, and you can have the same demonstration as a simulation if you use this code. And the code files can be downloaded from here. Before that, it is not allowed to download for the guest, but you can sign up using your Gmail, and then you can download. Once you download, there will be 2 external files called LCD 16 by 2 bit.h, and other one is .c. So you have to copy these 2 files onto your main folder, where your main file is there, and then only you can work it out. So I will show you how to do this in Admiral Studio. All right, so you can create a new file and a new project, and select this AVR microcontroller as Mega 16 and copy this code that is available on that website here. And if you try to build this one, so definitely you will get some compilation errors, right? Build is failed due to multiple error reasons. Okay. So because that is, you haven't included, even though you define this LCD.bit library, it is not imported to your project files, right? So first thing is you have to go to your folder and copy these .h and .c files on the same place where the main .c file is there, right? So you have to copy that. Even though you copied it, this at Mother Studio does not import that, right? So in that case, you can just right click and add existing item. And now you can see that I have copied this LCD2-bit C file and H file to this folder. But I can just select both of them and click add. Now you can see those two are added to my working folder. Now this will understand this line because these two files are imported to my working project library. So I will build this again. So it builds succeeded, which means it works fine. So that's how you, because we as like when you practicing coding, you don't always need to define another code for the LCD here on your main file. So that makes your program more complicated and looks messy. Instead, you can use external libraries, right? So if you take a look at this C library for this one, so the same things that we have done it for 8-bit operation, now it is for 4-bit operation. So you are just using a 4 pins of the LCD. And this is that LCD initialization and copying the data and everything is there. And there's a header file as well in the header file. So whatever the functions that you write here, so you have to define in your header file, right? And so this is how you define the header. Even in your header, you can define the clock frequency of your Atmega microcontroller. You don't need to define it in your main file. If you define it in the main file, you cannot redefine it again, right? Otherwise, it will show some warnings. And delays and everything can be included here. And so where you call your functions, so whatever the functions that you've written in here are declared in here. So basically you have to import these two files. Even if you copy in the same folder, you have to just import to your working project. Then you can compile it. So that's how you import external third-party libraries. That will be more helpful when you're writing codes. So there could be more and more libraries available for different applications. For example, now LCD is one application. If you want to use it for communications like I2C or USART or SPI, there could be some examples available on the internet where the people have already built these C and H files. So if they are trustable files, if you know they are working, you can see the comments of the people who has commented on those projects. So if they are working, you can just use them, right? So you don't need to build your own coding here. Instead, you can use them. So that will make your life easier. Otherwise, every time you have to write a LCD program, that makes the life a little bit time consuming. Instead, you can use these header files. So that's how you're going to use external libraries. The creating of these C files and H files out of the scope of this module. But instead, if someone is interested, I will share a YouTube video. You can refer to that video, how to create an external library and import it to your project. Here, what we done is like we just copied from that website and copied to our folder and imported to our working folder. Instead, you can create your own C and H files and get it using with your main code. So I will share example video. If you are interested, you can take a look, but that is out of the scope of this module. So that concludes this presentation, and I hope like everybody got a clear understanding about how to use DHT 11 temperature and humidity digital sensor and working with one wire communication, and how to import external libraries to your code if you want to simplify your programs. So thank you very much for listening. I hope you can use the knowledge that I have just given to you for your future projects.